Hello there, and welcome. I'm so glad you found your way here tonight. Maybe you've had a long day. Maybe your mind has been busy with thoughts that will not settle. Or maybe you simply prefer to fall asleep while thinking about the stars instead of counting sheep. Whatever brought you here, this video is made just for you. Let your body sink down wherever you're resting. Feel your shoulders drop. Let your breath slow down, becoming softer and quieter with each moment that passes. Allow your mind to grow lighter, as if gravity itself has decided to be gentler with you tonight. There is nothing you need to do right now, nothing you need to remember or worry about. You are exactly where you need to be. Tonight, we turn our attention to cosmology. This is the miraculous story of our universe. From the very first spark of light to the birth of giant galaxies, it is a tale filled with vastness, mystery, and wonder. Some of what you hear may surprise you. Some of it may simply spark a gentle sense of curiosity as you drift off to sleep. Either way, let it wash over you like a warm tide. If these calm explorations bring you peace, consider liking and subscribing to this channel. It helps others find their way here too, one sleepy soul at a time. But there is no pressure. For now, just let yourself be here. Let yourself rest. The universe is vast beyond imagination. It is older than we can truly understand. It is filled with light and darkness, with energy and emptiness, with motion and stillness. And somehow we are part of it. You are part of it. Every atom in your body was once inside a star. Every breath you take connects you to the earliest moments of creation. Now, let us begin our gentle drift through the cosmos. Let us explore the universe together, one soft fact at a time. Fact 1. The early universe may have been filled with light so dense it behaved like matter. In the very first instant after the beginning, the universe was not dark and it was not empty. Instead, it was radiant beyond anything we can picture. Photons, which are the particles of light, were packed so closely together that they could not move freely through space. They scattered constantly, bouncing off particles of matter and colliding with each other in an endless dance. This created something extraordinary. The light itself had pressure, almost as if it were a physical substance with weight and texture. It was not the empty, weightless light we see streaming through windows today. It was something heavier, denser, more real. Over time, as the cosmos expanded and cooled, these photons finally slipped free. They began streaming into space, creating what we now call the cosmic microwave background. That faint glow still surrounds us today, stretched out and cooled down by billions of years of expansion. It is the remnant of a universe that once shone so brightly that light itself behaved like solid matter. Fact 2. Some regions of the cosmos may still be inflating forever, cut off from us. Cosmic inflation is the idea that in its first fraction of a second, the universe expanded faster than the speed of light itself. This sounds impossible, but it is allowed by the laws of physics because it was space itself doing the expanding, not objects moving through space. According to some models, this inflation never stopped everywhere at once. Instead, it may continue eternally in distant pockets of reality, creating new regions of space-time forever. These inflating domains would expand so quickly that no light could ever cross the gulf between them and us. In this picture, our universe is just one bubble among countless others, each sealed off by the runaway expansion of space. We will never see those regions. We will never touch them. We will never send signals to them or receive messages from them. And yet they might exist, endlessly budding into the void like flowers blooming in an infinite garden. To think that our entire observable cosmos, with all its trillions of galaxies, could be just one finite blossom on an infinite tree is both humbling and strangely beautiful. Fact 3. Black holes could carry imprints of the universe's first moments. Black holes are usually thought of as the graves of stars, the final resting places of massive suns that have collapsed under their own weight. But some black holes might be far older than any star that has ever existed. Cosmologists have proposed the idea of primordial black holes, which would have formed in the chaos of the early universe. If density fluctuations in that fiery first second were strong enough, whole regions of space could have collapsed under their own gravity before atoms, stars, or galaxies ever came into being. Such black holes would carry with them clues to conditions right after the beginning. They could be as tiny as mountains or as massive as stars, hidden across the universe like relics of creation itself. If discovered, they would be time capsules holding secrets of a universe younger than a heartbeat, when physics itself may have followed rules different from those we know today. Fact 4. Time near the beginning may have flowed differently than it does now. Time feels steady to us. Each second ticks off evenly, one after another, like a reliable clock that never changes its rhythm. But near the beginning of the universe, things may not have been so simple. General relativity tells us that time and space are woven together into a single fabric, and their behavior depends on energy and gravity. In the seething furnace of the early universe, densities and energies were unimaginably high. Time itself may have stretched, warped, or slowed compared to the flow we experience today. Some theories suggest that what we call the beginning of time may not even have been the true beginning, but rather a transformation from one state to another. When we look back across billions of years, we may not just be peering through space, but also through changing rivers of time itself. The past may have had a different tempo, a different rhythm, a different way of unfolding moment by moment. Fact 5. The largest known structure in the universe is a billion light-year-long wave of galaxies. The universe is not uniform. Galaxies are not scattered randomly like dust thrown into the wind. Instead, they form vast patterns, threads, walls, and filaments that stretch across unimaginable distances. One of the most extraordinary of these is something called the Boss Great Wall, discovered through careful galaxy surveys. It is a sprawling chain of superclusters extending across nearly 1 billion light-years of space. Within it, galaxies are strung together like glowing beads on invisible strings of dark matter. To put its scale into perspective, if our Milky Way galaxy were a single dot on a map, this wall would stretch across entire pages. It would be like comparing a grain of sand to a city block. These structures remind us that the cosmos is not just vast, but also deeply patterned. There is a kind of architecture on the grandest imaginable stage, a design that emerges from the invisible hand of gravity working across billions of years. Fact 6. Neutrinos from the first second of creation are still streaming through your body. Neutrinos are ghostly particles, almost without mass, that rarely interact with matter. They are so elusive that trillions of them pass through your body every second, completely unnoticed. Many of these are made in the sun or distant stars, created by the nuclear reactions that make light and heat. But some neutrinos are unimaginably older. In the first second after the beginning, neutrinos flooded the universe in vast numbers. Unlike photons, which remain trapped for hundreds of thousands of years, neutrinos slipped free almost immediately because they interact so weakly with matter. They have been flying through space ever since, forming what physicists call the cosmic neutrino background. Though they are nearly impossible to detect, they are everywhere, including inside you right now. Each one is a relic of the universe's very first heartbeat, still whispering through the cosmos almost 14 billion years later. You are being touched by particles older than stars, older than galaxies, older than anything we can see with telescopes. Fact 7. Entire galaxies may be moving because of hidden masses beyond the observable edge. Astronomers have noticed something strange. Some galaxies are not drifting in the directions we would expect based on the matter we can see. Instead, they seem to be tugged along by a hidden influence, something lying far beyond the part of the universe we can observe. This motion has been nicknamed the dark flow, and it remains one of the most puzzling mysteries in cosmology. The dark flow may be caused by enormous masses outside our cosmic horizon, invisible to us but powerful enough to bend the paths of whole clusters of galaxies across hundreds of millions of light-years. We cannot observe these hidden regions directly. Light from them has not had time to reach us yet, but we can see their fingerprints in the motions of galaxies closer to us, galaxies that are being pulled like leaves on a slow current towards something we cannot see. It is a reminder that the observable universe is just a patch of something larger, and that unseen structures may still shape the cosmos we live in. Fact 8. The vacuum of space may not be empty, but simmering with quantum energy. When we picture empty space, we often imagine nothingness, a true void with absolutely nothing in it. But according to quantum theory, even the vacuum is restless. Tiny particles blink in and out of existence, borrowing energy from uncertainty itself before disappearing again in fractions of a second. This restless activity is called the quantum vacuum, and it may hold the key to one of the greatest mysteries in cosmology. Dark energy, the mysterious force driving the accelerated expansion of the universe, could be related to the energy of this empty space. In that sense, every cubic inch of apparent nothingness is alive with possibility, buzzing invisibly with the physics that shapes the fate of the cosmos. What we call empty may be the most active thing in the universe. Fact 9, patterns in the cosmic microwave background hint at ripples from before the beginning. The cosmic microwave background is the oldest light we can see, released when the universe was only hundreds of thousands of years old. To the eye, it looks almost uniform, a faint glow spread evenly across the entire sky. But sensitive maps reveal tiny variations, ripples less than 1 part in 100,000. These patterns seeded the galaxies, stars, and planets we know today. But some of the ripples are stranger than others. There are unusually cold spots and unusually aligned features that point to possible physics from before the beginning itself. They may be scars left from collisions with other universes, or echoes of exotic fields that shaped inflation in its earliest moments. The faint patterns in this ancient light are not just random noise. They may be the fingerprints of realities far older and larger than our own. Clues written into the sky about events that happened before time as we know it even began. Fact 10. The fate of the universe might depend on particles we have not discovered yet. The destiny of the cosmos, whether it expands forever, collapses back on itself, or drifts into heat death, depends on the nature of its most mysterious ingredients. Dark energy drives expansion, dark matter shapes galaxies, and both may be tied to particles we have never seen or detected. Physicists search for these unseen particles in underground detectors and high-energy colliders, hoping to glimpse the missing pieces of the puzzle. If they exist, they will tell us whether the universe is stable, whether it may someday decay into something else, or whether it might even cycle through endless rebirths. In the smallest particles may lie the largest answers, hidden keys to the story of everything. The future of all existence may rest on discoveries we have not yet made, on particles whose names we do not yet know. Fact 11. Gravity may be weaker than it should be because it leaks into other dimensions. We think of gravity as universal, the force that binds planets to stars and stars to galaxies. But compared to the other forces of nature, like electromagnetism or the nuclear forces, gravity is astonishingly weak. A small magnet can lift a paperclip against the gravitational pull of the entire Earth. This has puzzled physicists for a long time. Some wonder if gravity feels weak because it is not confined to our familiar 3 dimensions of space. Instead, it may spread into hidden dimensions that we cannot see or access. If true, this would mean the force we experience is only a faint echo of a deeper reality. These extra dimensions could be curled up, too small for us to perceive directly, yet large enough to siphon away most of gravity's strength. It is a hypothesis that may explain why the cosmos holds together the way it does, and a hint that our universe could be part of something more layered and complex than we can imagine. Fact 12. The cosmic horizon hides regions of the universe we can never reach. When we look out into the sky, we are really looking back in time. Light takes time to travel, so the farther away something is, the longer ago we're seeing it. But there is a limit, a boundary called the cosmic horizon. Beyond this line, light has not had enough time to reach us since the beginning. Those regions of space are real. They are filled with galaxies, stars, and planets, but they are forever hidden from our view. The horizon is not a wall or a barrier, it is simply a limit of perspective, like standing on a shore and seeing only as far as the curve of the Earth allows. Every year the horizon grows as light from farther reaches finally arrives. Yet space itself expands too, pushing other regions beyond our view, faster than light can catch up. The cosmic horizon is a quiet reminder that no matter how far our telescopes stretch, there will always be more universe beyond, forever out of sight. Fact 13. Primordial black holes could be as small as atoms or as heavy as mountains. Most black holes form when stars collapse at the end of their lives. but there may be older, stranger ones called primordial black holes. Born in the first moments after the beginning, they could be wildly different from the black holes we know today. Some may be tiny, with event horizons smaller than an atom, while others could weigh as much as entire mountains despite being incredibly small in size. Over billions of years, the smallest ones would have evaporated through a process called Hawking radiation, slowly leaking energy until they disappeared. But others might still drift invisibly through the cosmos, too small and too dark to see. If they exist, they could even make up some or all of the mysterious dark matter that shapes galaxies. These hidden relics would be scattered everywhere, silent fossils of creation itself. They could be so subtle that a primordial black hole could pass through Earth unnoticed, yet so powerful that collectively they may shape the destiny of galaxies. Fact 14. The early universe may have birthed cosmic strings stretching across space. Theories of high-energy physics predict that, as the universe cooled from its hot beginning, strange defects in space-time could have formed. These are called cosmic strings. Unlike ordinary strings, they are not made of matter at all. They are cracks in space-time itself, infinitely thin but immensely powerful, stretching potentially for billions of light-years across the cosmos. If two cosmic strings were to cross paths, they could snap and release bursts of gravitational waves, ringing through the universe like struck chords on an invisible instrument. Though none have yet been found, their existence would reveal physics far beyond what we currently know. The idea that the early universe might still hold hidden filaments, invisible to our eyes but etched into the fabric of space itself, is both haunting and beautiful. They would be like scars from the cosmos's own birth, permanent marks left by the universe's most violent transformations. Fact 15. Ripples in space-time could be fossils from the very first instant. Gravitational waves are ripples in space-time itself, stirred up by events like colliding black holes or neutron stars. We have detected these waves in recent years using incredibly sensitive instruments, but there may also be far older waves, born in the very first instant of the universe. During cosmic inflation, space-time itself may have shivered with quantum fluctuations. Those tiny shivers would have been stretched across the entire cosmos as space expanded. These primordial gravitational waves would be unimaginably faint, but if we could detect them, they would be direct fossils of the universe's birth. Unlike light, which only became free to travel hundreds of thousands of years later, these ripples would carry us back almost to time zero. Scientists search for them in delicate patterns of polarization in the cosmic microwave background, hoping to hear the faintest whispers of creation's first breath. If found, they would confirm inflation and give us a window into energies and conditions we could never reproduce on Earth. Fact 16. Some galaxies may be racing toward a mysterious great attractor hidden in space. Our galaxy, along with many others, is not just drifting aimlessly through space. It is being pulled toward a region called the Great Attractor. This hidden mass lies hundreds of millions of light-years away, shrouded behind the dust and stars of the Milky Way, making it difficult to study directly. Galaxies across vast distances show a shared motion, as though they are sliding down the slope of some invisible, gravitational hill. The true nature of the Great Attractor is still uncertain. It may be a concentration of galaxy clusters, or something even larger and more massive. Whatever it is, it exerts a pull strong enough to guide the paths of entire galaxies, including our own. We are moving toward it even now, carried along on the slow current of cosmic gravity. Someday, billions of years from now, we may arrive. But for now, it remains a mystery, a hidden destination written into the motion of countless galaxies. Fact 17. Dark energy might grow stronger with time, changing the universe's destiny. Dark energy is the mysterious force driving the accelerated expansion of the universe. For now, it seems steady and unchanging, but what if it is not constant? Some models suggest that dark energy could grow stronger over billions of years. If that happens, the expansion would accelerate more and more, eventually tearing galaxies apart, then stars, then planets, and finally even atoms themselves in a catastrophic event called the Big Rip. In other scenarios, dark energy could fade over time, allowing gravity to slow the expansion or even reverse it entirely. Because dark energy makes up most of the energy content of the cosmos, its behavior determines everything about the future. And yet for now, we do not know if it is constant or evolving. The entire fate of the universe may rest on the hidden nature of this invisible force that pushes everything apart. Fact 18. Cosmic voids, vast expanses with almost no galaxies, are still expanding. Between the luminous filaments of the cosmic web lie immense empty regions called voids. These can span hundreds of millions of light years and contain only a handful of galaxies scattered here and there. Voids are not static emptiness, though. They're expanding faster than the rest of the universe as matter flows outward toward denser regions. In a way, they are the growing hollows of the cosmos, ballooning as galaxies drift away from their centers. By studying these voids, scientists can test the nature of dark energy and cosmic expansion. For now, they remain among the quietest and loneliest regions of the universe. They are vast oceans of near nothing, still stretching wider as time moves on. To cross one would take hundreds of millions of years, even travelling at the speed of a light, and you would see almost nothing the entire journey. Fact 19. The universe's geometry may be ever so slightly curved. When we think of the universe, we often picture it as flat, stretching endlessly in all directions like an infinite sheet. But geometry in cosmology is subtle and surprising. Depending on its total energy, the universe could be positively curved like the surface of a sphere, or negatively curved like a saddle shape. Observations suggest it is astonishingly close to flat, so close that if there is any curvature at all, it is too small to detect with certainty using current instruments. A universe, with even the tiniest curvature, would, over unimaginable distances, bend light in ways that reveal its true shape. For now, we live in a cosmos that feels flat to us, but cosmologists keep searching for that faint hidden curve that could tell us more about its ultimate size and fate. If the universe is curved, it might be finite in size. If it is flat, it could go on forever. Fact 20. The cosmic microwave background is dotted with strange cold spots. The cosmic microwave background, the afterglow of the beginning, is mostly smooth and uniform across the entire sky. Yet here and there it contains unusual features, patches that are colder than expected. One of the largest is known simply as the cold spot, a region of the sky where the temperature of this ancient light dips strangely low. Some scientists suggest it may be caused by a massive void in that direction, sapping energy from photons as they pass through empty space. Others speculate it could be a fingerprint of physics beyond the known universe, perhaps even the scar of a collision with another cosmos. Whatever its cause, the cold spot remains one of the most puzzling anomalies written in the universe's oldest light. It is a small imperfection in an otherwise remarkably smooth sky, and imperfections like this often lead to the biggest discoveries. Fact 21. The first stars may have been hundreds of times heavier than the Sun. In the quiet darkness after the beginning, the universe eventually cooled enough for hydrogen and helium to gather together. Then came the very first stars. These were nothing like the stars we see today. With no heavier elements to cool the gas clouds, they grew enormous, hundreds of times the mass of our Sun. Their light was intense, blazing white and blue, and they lived fast, burning through their fuel in only a few million years. These population 3 stars forged the very first heavier elements, carbon, oxygen and iron, deep in their cores through nuclear fusion. When they died, they scattered those elements across space, seeding the raw material for later generations of stars, planets, and eventually life. Though none of these first stars remain today, every atom of carbon in your body may once have been born in one of these long-vanished giants. They were the universe's first makers, transforming simple elements into the building blocks of everything that would come after. Fact 22. Some of those first stars may have collapsed into the first black holes. The most massive of the first stars ended their short lives in spectacular collapse. Their gravity was so strong that when their fuel ran out, no force in the universe could stop them from imploding. Some exploded as supernovas, leaving behind dense neutron stars. But others fell directly into black holes, disappearing beyond an event horizon from which nothing can escape. These black holes were unique. They were not the corpses of ordinary stars, but the direct descendants of the first cosmic fire. They may have acted as seeds, growing over, billions of years through mergers and feeding, eventually becoming the supermassive black holes that anchor galaxies today. If this is true, then the brilliant quasars we see at the edge of the observable universe, powered by black holes a billion times the mass of the Sun, may trace their lineage all the way back to those first collapsing stars born in the dawn of time. Fact 23. The Milky Way moves through space at over 1,000,000 miles per hour. Though the night sky looks still and unchanging, our galaxy is on a ceaseless journey through the cosmos. The Milky Way, along with all its stars, planets and nebulae, drifts through the cosmic web at more than 1,000,000 miles per hour. This motion is partly the result of local gravitational pulls from nearby galaxies and clusters, and partly from vast unseen structures like the Great Attractor. To us, this incredible speed feels invisible because everything around us moves together. We are like passengers on a ship who cannot feel the motion because the entire vessel moves as one. But when astronomers measure the cosmic microwave background carefully, they can see a faint pattern caused by our galactic motion. It is a reminder that there is no absolute rest in the universe. Everything drifts, everything flows, everything is carried along in the great cosmic tide that has been moving since the beginning. Fact 24. Superclusters of galaxies weave a cosmic web across the universe. Galaxies do not sit alone in space like isolated islands. They gather into clusters, and those clusters gather into even larger structures called superclusters. These superclusters stretch for hundreds of millions of light years, linked by filaments of galaxies and dark matter, and separated by vast cosmic voids. Together they form the cosmic web, a pattern that resembles the strands of a spider's web or the filaments of neurons in a brain. Our own galaxy lives within something called the Laniakea supercluster, a sprawling region that contains hundreds of thousands of galaxies. When we map these structures across the sky, we see not chaos, but elegance. We see gravity sculpting luminous threads across the universe, revealing a hidden order that spans billions of light years. The cosmic web is the largest structure we know, and it continues to evolve and grow as the universe ages. Fact 25. Ancient quasars shine from less than 1,000,000,000 years after the beginning. Quasars are among the brightest beacons of the early universe. They are galaxies whose central black holes feed so hungrily that they blaze brighter than all their stars combined. Some quasars we see today come from less than 1,000,000,000 years after the beginning, when the cosmos was still remarkably young. To shine so brightly so soon, their black holes must have grown with astonishing speed, reaching masses of 1,000,000,000 suns in a fraction of cosmic history. These quasars act like lighthouses, illuminating the fog of intergalactic gas and helping us peer back into an era, called reionization, when galaxies first carved light into the darkness. Their existence poses deep questions. How did black holes grow so fast? What seeds gave rise to them? And what does their early appearance tell us about the conditions in the young universe? They remain mysteries wrapped in brilliant light, shining across billions of years to reach our telescopes today. Fact 26. We may live in a local bubble of unusually empty space. Astronomers mapping the material between stars have discovered something interesting. Our Sun lies within a vast cavity, a bubble carved into the galaxy's gas and dust. This local bubble stretches hundreds of light years across and is unusually empty compared to its surroundings. It was likely created by a chain of supernova explosions millions of years ago, which blew away the surrounding material in powerful waves. Today, our Sun and its neighbours drift quietly within this rarefied zone, bathed in a faint glow of hot plasma. The edges of the bubble form denser walls of gas and dust, where new stars are currently being born. To think that our solar system resides inside the lingering footprint of ancient stellar deaths adds a strange intimacy to our place in the cosmos. We live in a clearing made by stars that died long before our Sun was born. Fact 27. Dark matter may clump into invisible filaments that shape galaxies. When astronomers simulate the growth of the universe on computers, they find that ordinary matter alone cannot form the patterns we see in the night sky. Something unseen, something we call dark matter, must weave invisible scaffolding beneath it all. In these simulations, dark matter clumps into filaments stretching across space, guiding the flow of galaxies into strands and knots like beads on invisible threads. Our own Milky Way sits within one of these invisible filaments, held in place by gravity we cannot see. We cannot detect the dark matter directly with our telescopes, but we can see its gravity sculpting the grand architecture of the universe. Without it, galaxies would fly apart and the cosmic web would unravel into scattered fragments. Dark matter is the hidden skeleton on which all visible structure hangs. Fact 28. Axions, if they exist, could make up all dark matter. The true identity of dark matter is still unknown, one of the greatest mysteries in all of science. But one candidate is something called the axion, a hypothetical particle predicted by certain theories of quantum physics. Unlike the heavy particles once imagined to explain dark matter, axions would be incredibly light, lighter even than neutrinos. But they would be produced in such enormous numbers during the early universe that together they could outweigh all the visible matter in existence. Axions would interact so weakly with ordinary matter that they slip through stars, planets, and even the most sensitive detectors unnoticed. Scientists have built experiments with ultra-sensitive magnetic fields and resonant cavities, hoping to catch even a whisper of these elusive particles. If found, axions would not only solve the dark matter mystery, but also connect cosmology with deep questions of particle physics that have puzzled scientists for decades. Fact 29. The laws of physics may be slightly different in other universes. Some versions of inflation predict that our universe is only one bubble in an endless sea of universes, each born from eternal inflation. If this is true, then the laws of physics themselves may vary from bubble to bubble. In one universe, stars might never form because gravity is weaker than it is here. In another universe, atoms may not exist at all because the forces holding them together are different. Our own universe appears finely balanced, with its constants arranged in a way that allows galaxies, chemistry, and life to emerge. This raises a haunting possibility. Perhaps we live in one universe among countless others, most of them sterile and lifeless, some chaotic and violent, but ours balanced just enough for complexity to bloom. Though we cannot see beyond our cosmic horizon, the idea that reality may be broader than our laws allows us to wonder at the fragile conditions that make existence possible here. Fact 30. Cosmic inflation could have spawned an infinite multiverse. In the theory of eternal inflation, the universe does not expand as a single bubble, but as an endless froth of possibilities. Regions of space stop inflating and form universes like ours, while other regions keep expanding forever, spawning new bubbles constantly. Each bubble could be infinite in size on its own, and together they form a multiverse without end, an infinite collection of infinite universes. In this picture, the beginning was not the start of everything, but simply the birth of our local region. Other universes may lie forever beyond our reach, each with its own physics, its own galaxies, and perhaps its own forms of life. It is a vision of reality so vast that even our observable cosmos, with its 2 trillion galaxies, would be just one small ripple on an endless cosmic sea. The multiverse would be so large that the word infinite almost loses meaning. Fact 31. The universe once transitioned from opaque to transparent. For its first few 100,000 years, the universe was like a thick fog. It was filled with free electrons and protons drifting through space, scattering photons so completely that light could not travel more than a short distance. It was a glowing plasma, opaque to vision, with no way for radiation to move freely across space. Then, as the cosmos cooled, something remarkable happened. Electrons settled into orbits around protons, forming the first neutral atoms of hydrogen. Suddenly, photons were released from their constant scattering. They became able to fly unhindered across the universe. In that instant, the cosmos became transparent for the first time. The light we call the cosmic microwave background began its journey in that moment. Every time we measure that ancient glow today, we are seeing the moment the universe first let light go free, a timeless after-image of reality lifting its primordial veil. Fact 32. The reionization era lit up space with the first galaxies. After the universe became transparent, it entered a period that was clear but dark. Space was filled only with neutral hydrogen gas, and there were no stars yet to shine. For hundreds of millions of years, the cosmos was in a kind of dark age, waiting for something to ignite. Then slowly, the first galaxies began to form. Their newborn stars and brilliant quasars flooded space with ultraviolet light, energy powerful enough to break hydrogen atoms back into ions. This period is called the reionization era, when the fog lifted once more, but this time it was not lifted by cooling. It was pierced with light from within. Reionization carved great bubbles of transparency around the first galaxies, expanding outward until the whole universe was illuminated. When we observe distant galaxies and quasars today, we are catching sight of that moment when darkness gave way to cosmic dawn, and the universe became lit from within by its own creations. Fact 33. The cosmic neutrino background has never been directly seen. We know about the cosmic microwave background, the light from when the universe became transparent, but before that, another background formed, one that has never been directly detected. This is the sea of neutrinos released only seconds after the beginning. These ghostly particles still stream through space today, forming what scientists call the cosmic neutrino background. Unlike photons, which were trapped for hundreds of thousands of years by scattering, neutrinos escaped almost instantly because they interact so weakly with everything. They carry information from the universe's earliest heartbeat, from a time when the cosmos was less than a second old. Yet because they interact so weakly, we have never directly detected them. They flow through planets, stars, and our bodies almost without leaving any trace. Instruments capable of catching even a faint echo of this background are still being dreamed of and designed. If one day we do detect it, the cosmic neutrino background would be like opening a hidden window into the first second of existence itself. Fact 34. The most energetic particles in the universe may come from beyond our galaxy. Cosmic rays are high-energy particles that rain down on Earth constantly, striking our atmosphere with invisible impacts. Most come from sources within our own galaxy, like exploding stars called supernovas. But some cosmic rays carry energy so extreme that no known event in the Milky Way could have launched them. These ultra-high-energy cosmic rays may come from far beyond our galaxy, perhaps from the jets of distant quasars, or from collisions between entire galaxy clusters. Each particle travels for millions or even billions of years across the void, until by pure chance it meets Earth. When it strikes our atmosphere, it unleashes a cascade of secondary particles, creating momentary fireworks of energy that are invisible to the naked eye. Even now, we do not fully know what launches the most powerful particles in the universe. We only know that they come from somewhere far beyond our home galaxy, carrying messages from the most violent events in the cosmos. Fact 35. Black holes might merge often enough to reshape galaxies. Black holes are not always solitary objects drifting alone through space. In galaxies where stars are packed closely together and clusters interact, black holes can be drawn into pairs by gravity. Over time, they spiral closer and closer, radiating energy through gravitational waves until they finally merge into a single larger black hole. Each collision creates a burst of space-time ripples that spread outward at the speed of light. Over billions of years, these mergers may grow the black holes at the centers of galaxies to enormous sizes, sometimes reaching billions of times the mass of the Sun. When they do merge, the energy released can alter the flow of gas throughout the galaxy, shaping star formation and influencing the overall structure. In this way, black hole mergers are not just rare fireworks in the cosmic night. They are part of the quiet, ongoing architecture of the universe, chiseling galaxies into the shapes we see today. Fact 36. Gravitational waves carry whispers of ancient collisions. Einstein predicted their existence over a century ago, and after decades of searching, we finally heard them. Gravitational waves are ripples in space-time itself, created when massive objects like black holes or neutron stars collide. They stretch and squeeze space as they pass through it, though only by less than the width of a proton. With detectors like LIGO and Virgo, scientists have now recorded dozens of these events, distant cataclysms that happen billions of light-years away. Their whispers reach us across cosmic time, carrying signatures that tell us about the size, mass, and orbital dance of the objects that created them. Each detection is like hearing a bell ring from across the universe, and someday, if we can build even more sensitive instruments, we may catch the background hum of gravitational waves from the earliest universe itself, Echoes of creation still rolling through space-time like ripples on an infinite pond. Fact 37. The speed of cosmic expansion has changed more than once. The universe does not expand at a constant pace, like a car driving at steady speed down a highway. Instead, its rate of expansion has shifted dramatically over time. In its first fractions of a second, inflation drove an almost unimaginable burst of expansion, faster than the speed of light. After that phase ended, gravity began to slow things down as matter pulled against the outward flow of space. For billions of years, galaxies drifted apart at a gentle, decelerating rate, but the last few billion years, something changed. The expansion has sped up again, pushed by the mysterious force we call dark energy. This shifting pace tells us that the cosmos has gone through distinct phases, each governed by different balances of forces and energies within it. From rapid inflation to slow deceleration to present acceleration, the rhythm of expansion is like a cosmic heartbeat, changing with time and still unfolding into an unknown future. Fact 38. Some stars may have formed directly from collapsing dark matter. Ordinary stars form from collapsing clouds of hydrogen and helium gas. But some theories suggest a stranger origin story for certain objects in the early universe, something called dark stars. In the very young cosmos, dark matter may have clumped densely enough in certain places that its annihilation reactions released bursts of energy. Instead of collapsing fully into black holes, these clumps could have inflated into giant dark stars, powered not by nuclear fusion like ordinary stars, but by dark matter interactions themselves. They may have been massive beyond imagination, glowing faintly with heat generated from within their invisible cores. But unlike ordinary stars, their light would have been almost impossible for us to see. If such stars existed in the early universe, they could have been the first beacons of the cosmos, lighting up space before normal stars were born. Later they may have collapsed into black holes that seeded the growth of galaxies. Though still hypothetical, the idea of stars born from the invisible matter of the universe gives a haunting glimpse of what might once have been. Fact 39. The cosmic microwave background is slightly lopsided. When we map the cosmic microwave background across the entire sky, we find it is almost perfectly uniform in all directions. Almost, but not entirely. There is a slight asymmetry, a lopsidedness where one side of the sky shows slightly stronger fluctuations than the other. This imbalance is puzzling because the early universe should have been nearly the same in every direction, with no preferred orientation. Some explanations suggest it is simply a statistical fluke, a random chance that happened to occur in our particular region. Others propose deeper causes, like hidden physics from the inflation period, or even interactions with regions beyond our observable universe. Though subtle, this lopsidedness challenges our assumption that the cosmos is perfectly uniform at the larger scales. It keeps cosmologists searching for the hidden story behind this ancient light, wondering what it might reveal about conditions we cannot directly observe. Fact 40. A mysterious axis of evil aligns structures across the universe. Among the patterns of the cosmic microwave background, scientists have noticed something deeply unusual. Large-scale features seem to align along a common axis across the sky, as if the universe has a preferred direction. This alignment has been strangely nicknamed the axis of evil, though the name is more playful than serious. It should not exist if the universe is truly random and uniform at the larger scales, as our theories predict. Even more puzzling, some of the largest cosmic structures, like the distribution of galaxies, seem to follow this same orientation. Whether it is a coincidence, a statistical fluke, or a sign of unknown physics operating at cosmic scales, no one currently knows. The name may be playful, but the mystery is deeply serious. Why should the universe, so vast and ancient, show any preference for a particular direction at all? What could have set this alignment in motion? And what does it mean for our understanding of reality itself? Fact 41. The fine-tuning of cosmic constants allows galaxies to exist at all. The universe is balanced on what seems like a razor's edge. The strength of gravity, the charge of the electron, the mass of fundamental particles, all of these values appear to be set with remarkable precision. If any of them were even slightly different, the cosmos would look nothing like it does today. Stars might never ignite if nuclear forces were weaker. Atoms might never form if electromagnetic forces were stronger. Galaxies might collapse too quickly to allow anything interesting to develop if gravity were just a bit more powerful. This delicate balance is known as fine-tuning, and it fascinates cosmologists because it seems improbably precise. Some see it as a mystery to be explained by deeper laws of physics we have not yet discovered. Others suggest the multiverse, where countless universes exist with different values, and we simply live in one of the rare ones where conditions happen to allow observers like us to exist. Whatever the explanation, it is humbling to know that the entire visible universe, from the largest galaxy to the air in your lungs, depends on the delicate tuning of invisible constants written into the fabric of reality. Fact 42. Some physicists believe the universe is a hologram. It sounds like science fiction, but the holographic principle is a serious idea in theoretical physics. It suggests that everything in the universe, all the stars, galaxies, and even ourselves, might be described not in 3 dimensions, but by information encoded on a distant 2-dimensional surface. Just as a flat hologram can contain the illusion of depth and volume, the cosmos we live in may emerge from data written on a cosmic boundary somewhere beyond our reach. This strange idea comes from studying black holes, where information appears to be stored on the event horizon's surface rather than inside the volume. If this is true for black holes, some physicists argue it could be true for the whole universe. The holographic principle does not mean reality is an illusion or fake. It means that space and time themselves may be emergent phenomena, shadows cast by a deeper, more fundamental layer of physics that operates in ways we're only beginning to glimpse. Fact 43. Quantum fluctuations may have seeded every star and planet. At the smallest scales of reality, quantum physics rules everything. Particles flicker in and out of existence. Uncertainty is built into the fabric of nature. During cosmic inflation, these tiny quantum fluctuations were stretched to enormous scales by the rapid expansion of space. What began as microscopic jitters became slight ripples in the density of the universe, regions that were slightly more dense and regions that were slightly less dense. Over billions of years, gravity amplified those ripples. Matter was drawn into the denser regions more strongly, forming the seeds of galaxies, stars, and eventually planets. It is astonishing to realize that everything we see in the night sky, from the Milky Way to the most distant galaxy cluster, may have been born from microscopic quantum tremors amplified by the vast machinery of cosmic expansion. The entire universe, in a sense, rests on the chance vibrations of the quantum world, random fluctuations that happen to get stretched into the structures we call home. Fact 44. Cosmic inflation could have created baby universes we will never see. Inflation is the idea that the universe expanded faster than light in its first instant, but some versions of the theory suggest it did not happen uniformly everywhere. Instead, while our region slowed down and settled into the universe we know, other regions may have continued inflating, forming their own separate universes. This process may happen endlessly, with baby universes budding off like bubbles in boiling water. Each one would be cut off from the others by expansion so rapid that no signal, not even light, could cross between them. Some of these universes might follow laws of physics very different from ours. Others might look much the same, with galaxies and stars similar to what we see. If true, our observable universe is just one blossom on an infinite cosmic tree, with countless branches forever hidden from one another, each carrying its own version of reality, its own story, and perhaps its own forms of life wondering if they are alone. Fact 45. There may be more galaxies in the observable universe than grains of sand on Earth. The number of galaxies in the universe is almost beyond human comprehension. Early estimates from decades ago suggested hundreds of billions of galaxies, but deep field images from telescopes like Hubble, which stared at tiny patches of seemingly empty sky for weeks at a time, revealed far more structure than anyone expected. Counting carefully and extrapolating across the entire sky, cosmologists now think there may be around 2 trillion galaxies in the observable universe. To give perspective on this number, if you could somehow scoop up all the sand from every beach and every desert on Earth, counting every single grain, the total would still fall short of the number of galaxies above us. Each of those galaxies contains billions or even trillions of stars, and each of those stars could host planets, moons, and perhaps life. The scale is so immense that even the word infinite feels close at hand. When we gaze at the night sky, we see only the faintest sprinkling of the cosmic ocean, a handful of nearby sparks among an overwhelming abundance we can barely imagine. Fact 46. Some regions of space may have negative energy density. In most of the universe, energy is positive, tied to matter, radiation, and motion. But in quantum field theory, there are scenarios where the energy of space itself could dip below zero, creating regions of negative energy density. These exotic states are not like ordinary emptiness. They could warp space-time in unusual ways, potentially allowing shortcuts like wormholes or even stable configurations that might enable advanced propulsion. Though still deeply theoretical, negative energy has been glimpsed in tiny effects such as the Casimir force, where two metal plates placed extremely close together in a vacuum experience a slight attractive force due to quantum effects. If negative energy can exist in small ways in laboratory conditions, perhaps it can exist in a larger cosmic context as well. Negative energy density could be one of the strangest hidden features of the universe, rare and fleeting, but profound enough to reshape our understanding of what emptiness really means. Fact 47. Primordial black holes could explain dark matter. Dark matter remains one of the great unsolved mysteries of cosmology. It is invisible, undetectable, except through its gravitational influence on galaxies and clusters. One intriguing possibility is that dark matter is not made of exotic particles at all, but of black holes formed in the first moments after the beginning. These primordial black holes could range in size from asteroids to stars, scattered throughout the cosmos in vast numbers. Unlike ordinary black holes that form from dying stars, they would be fossils of the universe's earliest fluctuations, born when regions of space collapsed under their own gravity before atoms even existed. If enough of them exist, they could account for all the dark matter we observe shaping galaxies and clusters. Detecting them would not be easy because they emit no light. They could drift unseen through space, giving themselves away only through rare gravitational effects, like the bending of light from background stars. If confirmed, primordial black holes would tie two of the universe's greatest mysteries together in a single elegant explanation. Fact 48. A single photon could in theory stretch across the whole universe. Photons, the particles of light, are described by quantum mechanics as waves. And in principle, a single photon's wave function can extend indefinitely, stretching across vast distances without limit. In the expanding universe, light from the earliest times has been redshifted to longer and longer wavelengths by the stretching of space itself. Some of the photons, from the cosmic microwave background, now have wavelengths measured in millimeters, stretched by billions of years of expansion. In theory, though we cannot observe this directly, a photon could be spread so thin that its wave function spans the entire observable universe. This is not something we can measure or verify, but it shows how strange quantum mechanics becomes when applied to cosmic scales. Even a single particle of light might not be truly local or confined to one place, but instead could be rippling silently across billions of light years, connecting distant regions in ways we are only beginning to understand. Fact 49. Entropy ensures the cosmos will one day reach heat death. Entropy is the tendency for systems to move from order to disorder, from concentrated energy to dispersed energy. On Earth, it is why energy dissipates, why things break down over time, why hot coffee cools and ice melts. On the scale of the entire cosmos, entropy ensures that stars will eventually burn out, that galaxies will drift apart, and that all usable energy will gradually vanish. In the far future, trillions upon trillions of years from now, the universe may reach a state called heat death. This is not a fiery ending, but a fading into uniformity. Everything will be cold, dark, and uniform, with no gradients left to drive any change or process. It is not a sudden catastrophe, but a slow dissolution into perfect stillness. Though it sounds bleak, it is also deeply peaceful in its own way. A universe that once blazed with the fire of stars and galaxies, gently settling into perfect, eternal calm. Fact 50. Vacuum decay could, in principle, erase the universe instantly. According to some interpretations of particle physics, the vacuum state of our universe, the lowest energy state of empty space, may not be perfectly stable. If it turns out to be only metastable, like a ball balanced on a hilltop, then one day a tiny bubble of true vacuum could form somewhere in the cosmos. This bubble would expand at nearly the speed of light, and it would erase everything it touched, rewriting the laws of physics as it spread outward. We would never see it coming because the change would arrive faster than light could warn us. Though the idea sounds terrifying, it is largely hypothetical, and even if possible, the timescales involved are so vast as to be irrelevant to human existence, or even the existence of stars and galaxies. For now, it remains one of the most haunting possibilities in cosmology, a reminder that reality itself may not be permanent, but rather a delicate balance that could, in principle, collapse into something completely different. Fact 51. Cosmic rays constantly shower Earth with particles from distant space. Every moment of every day, invisible particles from space rain down on our planet. These are cosmic rays, high-energy fragments of atoms launched by distant supernovas, pulsars, or even entire galaxies far away. Most pass through our atmosphere, unnoticed, striking air molecules and scattering into showers of smaller particles that cascade downward. Some are so energetic that they challenge our understanding of physics, carrying more power than any particle accelerator on Earth could ever produce. You're touched by them constantly, though you never feel it. They slip through your body, through oceans, even through solid mountains without leaving a trace. In fact, a tiny fraction of the static noise in old film photography comes from cosmic rays striking the film emulsion. They are a reminder that Earth is not isolated in space, but bathed in a steady drizzle of particles born in the most violent corners of the universe, still reaching us across immense spans of time and distance. Fact 52. The observable universe is only a fraction of the whole. When we look out into the cosmos with our most powerful telescopes, the most distant light we can see comes from around 13.8 billion years ago. Yet because space has been expanding all this time, the observable universe now stretches much farther, about 93 billion light-years across from edge to edge. But this is not the full extent of reality, only the patch we're able to see from our particular location. Beyond the cosmic horizon lies more space, perhaps infinitely more, hidden behind the limit of how far light has had time to travel since the beginning. Entire galaxies, clusters, even colossal structures may lie forever outside our reach, existing but invisible to us. Some theorists suggest our observable universe is like a bubble in a vast inflating ocean of space. Others imagine countless bubbles, each sealed from the rest by the expansion of space itself. Whatever lies beyond our horizon, we may never know for certain. And yet just knowing the universe is larger than what we see fills the night sky with profound mystery. Fact 53. Galaxy clusters collide in slow-motion cosmic crashes. Clusters of galaxies are the largest bound structures in the universe, containing hundreds or even thousands of galaxies plus immense clouds of hot gas that glow in X-rays. When two clusters collide, the process unfolds over billions of years, so slowly that from our perspective it appears almost frozen in time. The galaxies themselves usually pass through each other without directly colliding because the space between individual stars is so vast. But their hot gas clouds slam together with tremendous force, heating up and glowing brilliantly as they compress. Meanwhile, the invisible dark matter halos surrounding each cluster glide past almost undisturbed, barely interacting at all. These collisions reshape the clusters dramatically, mixing their contents and altering their structures in profound ways. Some galaxies may be stripped of their gas, leaving them to fade into silence as their star formation shuts down. Seen across cosmic time, cluster mergers are like continental drift on Earth, but on scales we can barely comprehend, slow, inexorable and transformative, sculpting the architecture of the universe itself. Fact 54. The bullet cluster provides direct evidence for dark matter. One of the strongest pieces of evidence for the existence of dark matter comes from an extraordinary collision called the bullet cluster. Two galaxy clusters passed through each other at tremendous speed, and astronomers were able to study the aftermath in exquisite detail. The visible gas, which carries most of the normal matter and glows brightly in X-rays, slowed down dramatically during the collision and piled up in the middle. But when scientists measured where the gravitational mass actually was using a technique called gravitational lensing, they found something surprising. The galaxies themselves, and more importantly the gravitational mass revealed by how light bends around them, kept moving ahead, completely separated from the gas. This showed clearly that most of the mass was not in the hot gas we can see, but in something invisible that passed right through without slowing down. The bullet cluster has become a cosmic laboratory, a snapshot frozen in time that proves unseen matter outweighs the stars and gas we can observe. It is one of the clearest and most compelling windows into the existence of the invisible scaffolding that holds the universe together. Fact 55. Some galaxies are so faint they are almost invisible. Not every galaxy glitters brightly in telescopic images. Some, called ultra-diffuse galaxies, spread their stars so thinly across space that they look more like faint smudges than luminous cities of light. These galaxies may be as large as the Milky Way in terms of their overall size, but with only a tiny fraction of the stars, making them incredibly dim and difficult to detect. They are ghostly presences in the cosmic landscape, often discovered only through extremely sensitive surveys that can pick up their faint glow. Some of these galaxies appear to be rich in dark matter, with far more invisible mass than visible stars. Others strangely seem to lack dark matter almost entirely, which puzzles scientists and challenges our understanding of how galaxies form. Their faintness makes them fragile, easily disrupted by gravitational interactions with larger galaxies passing nearby. Yet their existence reveals that galaxies come in far more varieties than we once imagined, from blazing spirals packed with brilliant stars to nearly invisible shadows drifting quietly through the cosmic web. Fact 56. Giant elliptical galaxies may be the fossils of countless mergers. While spiral galaxies like our Milky Way are graceful and structured with elegant arms, elliptical galaxies are huge, rounded, and often appear rather dull and featureless. Yet their apparent simplicity hides a dramatic and violent past. Astronomers believe that giant elliptical galaxies are the products of countless mergers over billions of years. Galaxies collide and combine, their orderly spiral structures shredded and scrambled into amorphous rounded shapes. Star formation gradually slows and stops as gas is consumed or stripped away during these violent interactions, leaving behind populations of old red stars glowing faintly. These galaxies can grow to incredible sizes, containing trillions of stars and stretching across hundreds of thousands of light years. In dense galaxy clusters, they often dominate the center, sitting like massive monuments to an ancient and violent history. To gaze at a giant elliptical galaxy is not to see a quiet, unchanging giant, but rather the faded memory of countless galactic collisions written into its smooth, rounded glow. Fact 57. The universe may be shaped by physics we have not discovered yet. Our best models and theories explain much of what we observe in the cosmos, but cosmology still leans heavily on profound mysteries. Dark matter and dark energy together make up about 95% of the universe's total content, yet we still do not know what either of them actually is. Inflation, the theory that explains the early rapid expansion, still lacks a complete mechanism or explanation for what drove it. And quantum gravity, the unification of general relativity with quantum mechanics, remains undiscovered despite decades of theoretical work. It may be that entirely new physics, laws and principles we have not yet glimpsed underpin the entire structure of reality. Each new telescope, each new experiment pushes us closer to the edge of the known, hinting that the universe may rest on foundations we have not yet uncovered. For now, cosmology stands as a bridge between the known and the unknown, a map sketched partly in solid discovery and partly in tantalizing mystery. Fact 58. Wormholes are allowed by relativity but may never form naturally. Einstein's equations of general relativity admit strange and exotic solutions, including tunnels through space-time that could potentially connect distant regions of the universe or even link different universes entirely. These theoretical structures are called wormholes, and they have become a beloved staple of science fiction stories. However, for a wormhole to remain open and traversable, it would require something called exotic matter, which has negative energy density, something we have never observed in large amounts or learned how to create. Without it, any wormhole that might theoretically form would collapse instantly, becoming impassable and essentially useless. Still, they remain a tantalizing thought experiment, a reminder that general relativity describes not just the universe we see, but also strange possibilities that stretch the imagination. Even if nature never built a wormhole and perhaps never will, they remain a reminder that the laws of physics allow for hidden corridors through the deep fabric of space-time itself. Fact 59. The cosmic web resembles the neural structure of a brain. When scientists create detailed maps of the large-scale structure of the universe, they find galaxies arranged in an intricate pattern of filaments, nodes, and voids. This arrangement is known as the cosmic web, and it bears a striking resemblance to another complex network, the structure of neurons in the human brain. Both systems balance concentrated nodes with connecting pathways in ways that seem to maximize the efficiency of flow and communication. In the brain, electrical signals travel along neural pathways. In the cosmos, matter and gravity flow along galactic filaments. The resemblance is not just visual either. Mathematically, the two networks share similar statistical properties and organizational principles. To think that the universe on its largest imaginable scales echoes the same architecture as the mind that contemplates it is a poetic coincidence. It is a reminder that certain patterns repeat across nature, from the smallest sparks of thought inside our heads to the vast sweep of galaxies stretching across billions of light years. Fact 60 supervoids may cause subtle distortions in cosmic light. A supervoid is an immense underdense region of space, larger and emptier than ordinary cosmic voids, spanning hundreds of millions of light-years across. Though nearly empty of matter, these supervoids still influence light passing through them in subtle ways. Photons travelling across a supervoid lose a tiny amount of energy due to the expansion of space, arriving at our telescopes slightly cooler than they would otherwise be. This subtle effect, known as the integrated Sachs-Wolf effect, leaves faint imprints on the cosmic microwave background. One possible explanation for the mysterious cold spot in that ancient light is that photons pass through an enormous supervoid on their journey to Earth, cooling slightly along the way. Though invisible themselves and containing almost no matter, supervoids may shape the universe's faintest signals in measurable ways. They are reminders that even vast regions of apparent emptiness can leave fingerprints on the oldest light in existence. Fact 61. Some galaxy clusters contain hot gas that outweighs their stars. When astronomers study galaxy clusters using multiple wavelengths of light, they discover something surprising. The stars we see, all the brilliant points of light in the galaxies themselves, make up only a small fraction of the cluster's total mass. Much more of the visible matter is actually locked in immense clouds of superheated gas that fill the space between galaxies. This gas reaches temperatures of tens of millions of degrees, so hot that it glows brilliantly in X-ray wavelengths invisible to our eyes. In many clusters, this hot gas outweighs all the stars combined by a significant margin. The gas is held in place by the cluster's powerful gravity, filling the space between galaxies like an invisible ocean. Without X-ray telescopes, we would never know this vast reservoir of matter was there at all. Its sheer mass reveals that galaxies are not isolated, islands floating in empty space, but rather members of vast ecosystems immersed in hot glowing atmospheres that extend far beyond the visible stars. Fact 62. Black holes may influence the fate of entire galaxies. Though incredibly tiny compared to the galaxies that host them, the supermassive black holes at galactic centers wield enormous influence over their surroundings. When these black holes feed on nearby matter, material spirals inward in a swirling disk, heating up until it releases torrents of radiation and powerful jets of particles that stream outward at nearly the speed of light. These outbursts can blow vast amounts of gas completely out of the galaxy, effectively shutting down star formation across the entire system. Alternatively, the energy released can stir up existing gas clouds, compressing them and triggering new waves of star formation. Over billions of years, the activity of a single supermassive black hole can regulate the growth and evolution of its host galaxy in profound ways. Observations reveal that the masses of central black holes and the properties of their host galaxies are tightly linked, as if they grow together in a cosmic dance shaping one another's destinies. Black holes, once thought to be purely destructive outliers, are now understood to be key architects of the cosmic landscape we observe. Fact 63. Time may pass at different rates in different cosmic regions. Einstein's theory of general relativity showed us something profound and counterintuitive. Time is not absolute or universal. It bends and flexes depending on gravity and motion. In regions near massive objects like black holes or neutron stars, time passes more slowly compared to regions with weaker gravity. On cosmic scales, this means the flow of time may differ slightly from place to place across the universe. Even the expansion of space itself affects time, stretching and altering the pace at which distant galaxies evolve compared to our local frame of reference. When we look at the cosmos through our telescopes, we are not just peering across vast distances of space. We are also looking across different rivers of time, each flowing at its own tempo determined by local conditions. The night sky is therefore not a single frozen snapshot, but rather a patchwork quilt of different timescales woven together into the grand cosmic story, each region ticking at its own rate. Fact 64. The speed of light sets a fundamental limit on what we can know. Light travels incredibly fast, nearly 300,000 kilometers every second. But despite this tremendous speed, it is not infinite. Because light has a finite speed and the universe has a finite age, we can only see light that has had enough time to reach us since the beginning. The farther we look into space, the further back in time we see, until we reach a natural boundary called the cosmic horizon. Beyond this horizon, light simply has not yet had time to arrive at Earth. This limit is not merely technological, something we might overcome with better instruments. It is fundamental, built into the very structure of space-time itself. No future telescope, no matter how advanced, can reveal what lies past the cosmic horizon. We live within this light-bound bubble, able to peer into the past but never beyond a certain edge. The speed of light, so constant and universal throughout physics, becomes not just a property of electromagnetic radiation, but a cosmic boundary on human understanding itself. Fact 65. The Planck era, the universe's first fraction of a second, remains a mystery. Cosmologists can describe the universe with reasonable confidence from about a trillionth of a second after the beginning onward. But the very first instant, known as the Planck era, remains completely hidden from our understanding. In this unimaginably brief sliver of time, less than 1 divided by 10 followed by 43 zeros of a second after the beginning, the universe was so hot and dense that our current theories of physics completely break down. Gravity, quantum mechanics, space-time and energy were all entwined together in ways we simply cannot model with existing mathematics. To understand this era would require a complete theory of quantum gravity, successfully uniting general relativity with the quantum world, something physicists have been pursuing for decades without success. For now, the Planck era remains a blank space on our cosmic timeline, the hidden prologue to the universe's story. Whatever happened during those first incomprehensible moments determined everything that followed. The laws of physics, the constants of nature, the seeds of structure. Yet it remains one of the deepest mysteries in all of science. Fact 66. Hawking radiation could one day evaporate black holes completely. Black holes seem like eternal prisons from which nothing can ever escape, not even light itself. But the brilliant physicist Stephen Hawking showed that they are not perfectly black after all. Quantum effects near the event horizon allow black holes to emit tiny amounts of radiation, now called Hawking radiation in his honour. This process is incredibly slow for the black holes we observe today. But over unimaginable timescales, far longer than the current age of the universe, this radiation slowly saps away their mass. For stellar mass black holes, the process would take longer than we can comprehend. But given enough time, trillions upon trillions upon trillions of years, they will eventually evaporate entirely, shrinking smaller and smaller until they disappear in a final burst of energy. Even the supermassive black holes at the hearts of galaxies will one day fade away into nothing but faint radiation. In the far distant future, when all the stars have long since burned out, Hawking radiation will be among the last whispers of the cosmos, as black holes themselves gently dissolve into silence. Fact 67. White holes are a possible mirror image of black holes. If Black holes are regions of space-time where nothing can escape once it crosses the event horizon. Then white holes would be their exact opposite, regions where nothing can enter but everything flows outward. They are mathematical solutions to Einstein's equations, mirror twins of black holes that emerge naturally from the mathematics of general relativity. A white hole would continuously spew matter and light outward, but would resist anything trying to cross its horizon from the outside. None have ever been observed in nature, and most physicists doubt they actually exist in the real universe. Still, they remain fascinating hypothetical objects. Some theories even suggest that black holes might somehow transform into white holes at the end of their extremely long lives, releasing information back into the universe that was previously thought lost forever. Though purely speculative and likely unphysical, white holes remind us of how strange and flexible the mathematics of relativity can be, allowing possibilities that stretch the imagination far beyond the familiar structures we observe. Fact 68. Some theories predict a cyclic universe that dies and is reborn. Not all cosmologists accept that the universe began once and for all with a single beginning and will end in a single fate. Some models suggest instead a cyclic pattern, where the universe expands, eventually slows down, reverses direction, and collapses back on itself. In this view, after reaching maximum expansion, the universe would contract in what might be called a big crunch. But rather than ending completely, this collapse might somehow trigger a new beginning, launching another cycle of expansion. This idea is ancient, echoed in myths and philosophies about eternal return, but it also has modern scientific formulations. Though evidence for a cyclic universe remains uncertain and controversial, the possibility is deeply compelling. It suggests that the cosmos is not a singular story, with a clear beginning and end, but rather an endless loop of deaths and rebirths, each universe perhaps slightly different from the last, unfolding perhaps forever in an eternal cosmic rhythm. Fact 69. A big crunch could one day reverse cosmic expansion. If the gravitational pull of all the matter in the universe was strong enough, it could eventually halt the expansion of space and reverse it entirely. Galaxies would slow their outward motion, pause, and then begin to collapse inward toward each other. The universe would start shrinking back on itself. Stars would crowd closer together. Galaxies would merge more frequently. Temperatures would begin to rise as space compressed. Eventually, if this process continued, everything would converge back together in a final catastrophic collapse called the Big Crunch, essentially undoing the initial expansion. For now, all current evidence suggests the opposite is happening. The universe is actually accelerating its expansion under the influence of dark energy. But the Big Crunch remains one possible fate, a cosmic implosion that would erase the universe we know, perhaps setting the stage for something entirely new to emerge from the wreckage. Fact 70. The Big Bounce could mean our universe is not the first. Some cosmologists have combined the ideas of expansion and contraction into a larger model called the Big Bounce. In this scenario, each universe expands, reaches a maximum size, contracts back down, but then instead of ending completely, it rebounds into a new expansion phase, like a cosmic heartbeat or a ball bouncing eternally. If this model is correct, then our universe is not the first to exist, but simply the latest in an endless chain of universes, each one following the one before. Each bounce might leave subtle traces imprinted in physical laws or patterns in the cosmic microwave background, faint signatures or asymmetries that careful observations might someday detect. The Big Bounce offers a kind of comforting symmetry to existence, where creation and destruction are not opposites but parts of an eternal rhythm, with no true beginning or final end. It is highly speculative but philosophically beautiful, suggesting that the cosmos breathes in and out forever, with our universe as just one breath among infinite others stretching backward and forward through eternity. Fact 71. Cosmic background radiation once glowed bright orange in the sky. The cosmic microwave background today appears as faint, cold radiation, barely above absolute zero in temperature. But billions of years ago, when the universe was younger and smaller, this same radiation was much warmer and appeared very different. If we could travel back in time to the early universe, this background radiation would have been warm enough to glow in visible wavelengths. the entire sky in every direction would have shone with a fiery orange glow, a uniform radiance stretching from horizon to horizon, with no stars, no galaxies, nothing but this all-encompassing light. Over time, as the cosmos expanded, the wavelengths of this light stretched longer and longer, cooling from visible orange light into invisible microwaves. That ancient orange glow was the universe itself shining, not from stars, but from the fabric of space-time itself in its youth. Today we can only detect it with sensitive radio telescopes, but once upon a time, the entire cosmos would have bathed everything in warm glowing light. Fact 72. The universe cooled as it expanded, allowing atoms to form. In the very beginning, immediately after the initial expansion started, the cosmos was far too hot for stable atoms to exist. The temperature was so extreme that protons and electrons could not bind together. They roamed freely through space as a plasma, constantly being torn apart by violent collisions. But as the universe expanded, its temperature steadily dropped, following the laws of thermodynamics. Eventually, around 380,000 years after the beginning, conditions became cool enough for a profound change to occur. Electrons could finally settle into stable orbits around protons, creating the first neutral hydrogen atoms. With atoms now stable, photons of light could travel freely for the first time, no longer constantly scattered by free electrons. This marked the end of the universe's chaotic childhood, the moment matter began to take recognizable form. Every atom of hydrogen in your body today, every atom in water, in air, in living things, in distant stars, is a direct descendant of that cosmic cooling when the universe first settled into organized structure. Fact 73. Matter barely won over antimatter in the beginning. In the earliest moments of creation, particles of matter and their antimatter twins were produced in nearly equal amounts. When matter and antimatter meet, they annihilate each other completely, converting their mass into pure energy and leaving nothing behind but light. Had the amounts been perfectly balanced, the universe today would contain no galaxies, no stars, no planets, and no life. There would be nothing but radiation spreading through empty space forever. But somehow, for reasons we still do not fully understand, matter held the slightest advantage over antimatter. For every billion particles of antimatter, there were about 1,000,000,001 particles of matter. That tiny imbalance, just one extra particle out of every billion, became everything we see today. All the stars, planets, oceans, mountains, and living things owe their existence to this microscopic asymmetry. The mystery of why matter triumphed over antimatter remains one of the great unsolved questions in physics, but the fact that it did is literally why anything exists at all. Fact 74. Without that imbalance, no galaxies would exist. It is almost impossible to overstate how fragile the existence of matter truly is. If the balance between matter and antimatter had been perfectly symmetrical in the early universe, their mutual destruction would have been total and complete. The universe would have become nothing but a thin haze of radiation, photons spreading outward forever through expanding space. No clumps of matter would have formed, no gravity would have pulled things together, no stars would ever have ignited, no galaxies would ever have assembled, no planets could have formed, and certainly no life could have arisen to wonder about any of it. Every structure we observe in existence, from the smallest grain of sand to the largest galaxy cluster, rests on that 1/1000,000th advantage of matter over antimatter. We owe our very being to what seems like a cosmic imperfection, the smallest possible break from perfect symmetry. The universe as we know it is built not on balance and symmetry, but on the tiniest imaginable departure from it. Fact 75. Inflation predicts the universe is nearly perfectly flat. The theory of cosmic inflation, which proposes that the universe expanded faster than light in its first instant, has another remarkable consequence beyond explaining uniformity. Inflation stretches and smooths everything it touches. Just as blowing up a balloon makes its surface appear flatter and flatter from up close, inflation stretched the fabric of space-time so enormously that today the universe appears nearly perfectly flat on all observable scales. Measurements of the cosmic microwave background have confirmed this prediction with remarkable precision. To within fractions of a percent, the geometry of space appears flat, showing no detectable curvature in any direction. Whether this flatness extends beyond our cosmic horizon, or whether the larger universe curves gently like a hidden sphere, remains unknown to us. But within our observable bubble, inflation has left behind a universe that is astonishingly straight and geometrically balanced, a testament to the incredible stretching that occurred in the first tiny fraction of a second. Fact 76. Dark flow hints at influences beyond our cosmic horizon. Astronomers studying the motion of galaxy clusters across vast regions of space discovered something deeply puzzling and unexpected. Many clusters, spread across enormous distances, seem to be drifting in the same general direction, moving faster and more uniformly than our standard models of cosmic structure would predict. This large-scale, coherent motion has been nicknamed dark flow, and it suggests something truly extraordinary about the nature of reality. There may be massive structures existing outside our observable universe, beyond the cosmic horizon where light has not yet had time to reach us, yet their gravity is so incredibly powerful that it tugs on galaxies across billions of light-years of space. If this interpretation is correct, then dark flow is not just an unusual motion pattern or statistical anomaly. It is direct observational evidence that our observable bubble is embedded in a much larger reality, one containing hidden giants and unseen structures that actively shape what we can see from our limited vantage point. Though the phenomenon remains hotly debated among cosmologists and not yet fully understood or confirmed, the idea that unseen structures beyond our cosmic edge are actively influencing the galaxies around us adds a haunting depth to our understanding of the night sky and our place within the greater whole. We may be feeling the gravitational pull of regions we will never ever be able to see. Fact 77. The integrated Sachs-Wolf effect reveals dark energy's fingerprints. Light from the cosmic microwave background does not travel through completely empty space on its long journey to reach us across billions of years. Instead, it weaves and winds its way past galaxies, clusters, and vast structures, gaining and losing tiny amounts of energy as it climbs out of and falls into gravitational wells along the way. In a universe without dark energy, where expansion was steadily slowing down under the pull of gravity, these small gains and losses of energy would cancel out perfectly over the course of the journey, leaving no net effect that we could measure. But careful observations reveal a small leftover signal that should not be there according to that simple model, something scientists call the integrated Sachs-Wolf effect. This subtle signature tells us something profound. It reveals that the gravitational wells themselves are actually changing as the universe expands, being stretched, weakened, and altered by the accelerating expansion driven by mysterious dark energy. In this faint but definitely measurable way, the invisible hand of dark energy leaves its fingerprints on the oldest light in existence, the cosmic microwave background. By carefully studying these delicate imprints in temperature patterns across the sky, mapping how photons were affected as they passed through evolving structures, scientists can confirm not only that dark energy exists as a real phenomenon, but that it has been actively shaping the evolution of cosmic structure for billions upon billions of years. It is like reading a message written in the faintest ink, but once you know how to look, the signature is unmistakable. Fact 78. The cosmic microwave background once fit inside your hand. Today, when we talk about the cosmic microwave background, we are describing radiation that fills the entire observable universe, spanning an incredible 93 billion light-years from edge to edge in all directions. It is everywhere we look, surrounding us completely, a faint whisper of ancient light arriving from every point in the sky simultaneously. But when that light was first released into space, when electrons and protons finally combined to form the first neutral atoms and photons, became free to travel unimpeded for the first time, the universe itself was much, much smaller than it is today. At that specific moment, about 380,000 years after the beginning, the entire cosmos was only about 1 million light-years across. To put that enormous-sounding number into perspective, that is actually quite small in cosmic terms, small enough that you could theoretically hold a sphere representing the whole universe in your outstretched hands. Imagine that for a moment. Imagine cradling the entire universe in your palms like a glowing ball, a sphere of hot plasma ready to expand into everything we know today, every galaxy and star and planet that would ever exist. That light, released when the universe was small enough to embrace, has been travelling ever since through expanding space, stretched and cooled by billions of years of cosmic expansion, but still present everywhere around us, still whispering its ancient story across the sky to anyone with instruments sensitive enough to listen. To think that the vast cosmos we inhabit, with its trillions of galaxies stretching beyond comprehension, was once compact enough to fit into a space you could theoretically embrace is almost impossible for the mind to truly grasp, and yet in its earliest moments, everything really did occupy such an incredibly small volume. Fact 79. Some ancient stars may still burn from the dawn of time. Most of the very first stars that ever formed were massive giants, hundreds of times heavier than our Sun, burning brilliantly but briefly like cosmic fireworks. These population 3 stars died out within just a few million years, exploding as supernovas or collapsing into black holes. However, a few of those earlier stars may have been quite different. Some may have been small, faint, and extraordinarily long-lived, the cosmic equivalent of candles that burn slowly and steadily. Stars with very low mass burn their nuclear fuel so slowly and efficiently that they can shine for trillions of years, far, far longer than the current age of the universe, which is less than 14 billion years old. Their nuclear reactions proceed at such a gentle pace that they can sustain themselves almost indefinitely. If any such small stars formed in the early cosmos during the first or second generation of star formation, they could still be burning today, scattered somewhere among the countless younger stars that fill galaxies. They would be dim and red, glowing softly in wavelengths our eyes cannot see, incredibly difficult to spot among the brighter stars that surround them. But if astronomers could somehow find and identify them with certainty, these ancient stars would be living fossils of the cosmic dawn, objects that have personally witnessed the birth of the first galaxies, the formation of the first planets, the growth of supermassive black holes, and the entire long unfolding of cosmic history across 13 billion years. Somewhere in the night sky above us, hidden in plain sight, a faint red ember may still glow today, older than almost anything else we have ever observed or ever will observe. Fact 80. The universe may still echo with the first gravitational waves. Gravitational waves are ripples in the fabric of space-time itself, distortions that travel at the speed of light carrying information about the violent events that created them. We have now detected dozens of these waves from colliding black holes and neutron stars in recent years, but some of the very first gravitational waves ever produced may have been generated during the period of cosmic inflation, in the first tiny fraction of a second after the beginning. These primordial gravitational waves would have been created by quantum fluctuations in the incredibly energetic and turbulent conditions of the infant universe, microscopic tremors in space-time amplified by the rapid expansion into cosmic-scale ripples. If they exist, they would have left faint imprints in a very specific pattern of polarization in the cosmic microwave background, a distinctive swirling signature that sophisticated telescopes are actively searching for right now. Detecting these ancient waves would be like hearing the faint sound of creation itself echoing across time, vibrations from the universe's earliest instant still ringing today across 13.8 billion years. Though they remain frustratingly elusive and have not yet been conclusively found despite intensive searches, experiments and observatories continue to push the boundaries of sensitivity, searching with ever greater precision for this background hum of primordial gravitational radiation. If discovered and confirmed, these primordial waves would directly verify the theory of inflation and give us concrete evidence of physics operating at energy scales we could never hope to reproduce in any laboratory on Earth, no matter how advanced our technology becomes. The cosmos itself would become our ultimate physics laboratory, still echoing with the reverberations of its own violent birth. Fact 81. The scale of cosmic expansion stretches light into red wavelengths. As the universe expands over billions of years, driven by the mysterious pressure of dark energy, it does not just stretch space itself, increasing the distances between galaxies. It also stretches the very light that travels through that expanding space, affecting every photon on its journey. Photons moving across billions of years through expanding space are gradually pulled to longer and longer wavelengths, systematically shifting toward the red end of the electromagnetic spectrum. This cosmological redshift is one of the primary tools astronomers use to measure distances to galaxies and determine how fast the universe is expanding at different epochs. The farther away a galaxy is from us in space, the longer its light has been travelling through expanding space, and therefore the more its light has been stretched during its journey, making it appear redder in our telescopes and instruments. This means the night sky is effectively a time machine painted in colours that tell us about distance and history. A galaxy that once shone brilliant blue in its youth, blazing with hot young stars, may now arrive at our instruments bathed in deep shades of red, its energy diluted and its wavelengths lengthened by billions of years of cosmic expansion. Each individual photon reaching your eye or striking a telescope detector tonight is an ancient traveller, stretched and drawn out like a musical note played slower and lower on an instrument, carrying within it the encoded story of distance, time, and the restless growth of the universe itself over cosmic ages. Fact 82. Olbers' paradox asks why the night sky is dark. Here is a simple thought experiment that puzzled some of the greatest minds in astronomy and philosophy for centuries. If the universe were truly infinite in both size and age, extending forever in all directions and having existed forever in time, and if it were filled relatively uniformly with stars in every direction, stretching endlessly into the distance, then the night sky should blaze with brilliant light everywhere we look. No matter which direction you turned your gaze, your line of sight would eventually intersect with the surface of a star somewhere in that infinite expanse, making the entire sky appear as bright as the surface of the sun itself, glowing uniformly without any dark spaces whatsoever. This deceptively simple thought experiment is known as Olbers' paradox, named after the astronomer Heinrich Olbers who popularized it, though others had pondered the question before him. Why then is the sky actually dark at night, with vast stretches of profound blackness between the scattered points of starlight we see? Why do we see darkness at all if the universe is infinite and eternal? The answer to this ancient puzzle lies in two fundamental facts about our universe that were not understood until relatively recently in human history. First, the cosmos has a finite age rather than being eternal. It began less than 14 billion years ago, meaning stars have not existed forever, and their light has not had infinite time to fill every corner of space. Second, the universe is not static and unchanging as once believed, but rather expanding continuously, which stretches light from the most distant sources into longer wavelengths that become invisible to our eyes, shifted into infrared and radio waves we cannot see without special instruments. The darkness between the stars is therefore not simply emptiness or absence of anything. It is a profound canvas painted by the twin effects of finite time and cosmic expansion, revealing to us that we live in a young, dynamic, evolving cosmos rather than an eternal, unchanging, static universe. Fact 83. The answer lies in cosmic expansion and finite age. The darkness we see when we look up at the night sky, the vast black spaces between the pinpricks of starlight, tells a profound story about the nature of reality itself. The universe is not static, frozen in place for all eternity like a painted backdrop. Instead, it is expanding dynamically, with galaxies receding from each other at speeds that increase steadily with distance, following a relationship discovered by Edwin Hubble nearly a century ago. This expansion means that light from the most distant galaxies is redshifted dramatically into wavelengths we cannot perceive with our eyes, stretched beyond the visible spectrum into infrared and radio wavelengths that require special detectors. The most distant galaxies are moving away so fast that their light arrives incredibly dimmed and reddened, contributing almost nothing to the brightness of the night sky. Additionally, and just as importantly, the universe has existed for only a finite amount of time, less than 14 billion years since the beginning. Light from regions beyond a certain distance, about 46 billion light-years away in terms of current distance, simply has not had enough time to reach us yet since the beginning occurred. That light is still on its way, travelling toward us through space, but it has not arrived yet and will not arrive for billions more years. Together, these two fundamental principles, cosmic expansion and finite age, completely resolve the ancient paradox. The universe is not infinitely old, nor is it static and unchanging as philosophers once assumed. Each patch of blackness above us is like a veil or curtain, hiding regions too distant or too early in cosmic history for their light to have completed the journey to Earth. The starless darkness between points of light is not truly empty or devoid of anything. It is alive with light still making its long way toward us, photons that were emitted billions of years ago and are still travelling, destined to arrive only after billions more years have passed, long after human civilization has faded into the depths of cosmic history. Fact 84. The universe may have begun as a quantum fluctuation. In the profoundly strange world of quantum physics, which governs the behaviour of reality at the smallest scales, empty space is never truly still, calm, or empty. Tiny fluctuations in energy constantly arise and disappear in what appears to be a vacuum, popping spontaneously in and out of existence in mere fractions of a second, borrowing energy from the fundamental uncertainty built into quantum mechanics. These are not just theoretical abstractions, but real effects that have been measured and observed in laboratories. Some theories, developed by physicists trying to understand what might have preceded or caused the beginning, suggest that the entire universe itself may have sprung from one such quantum fluctuation, a microscopic tremor or bubble in the fabric of nothingness that was somehow magnified and inflated by cosmic inflation into an entire cosmos. If this interpretation is true, then our universe is not a miraculous exception to the laws of physics requiring special explanation, but rather a completely natural outcome of those laws operating as they always do, a possibility that was eventually realized among infinite quantum rolls of the dice, occurring constantly in the underlying quantum foam of reality. The idea that everything we see around us, all the galaxies with their billions of stars, all the planets, all the complexity and beauty and life itself, grew from a microscopic flicker of quantum energy lasting less than the blink of an eye is both deeply humbling and profoundly awe-inspiring at the same time. It means the grandest scales of existence, spanning billions of light years and containing structures almost too large to comprehend, may be fundamentally rooted in the smallest and most fleeting whispers of quantum chance, operating at scales far, far smaller than atoms or even subatomic particles. Fact 85. Vacuum energy could drive both inflation and dark energy. Vacuum energy, sometimes called the energy of empty space, is the background energy that arises from quantum effects even in regions of space, containing absolutely no matter or radiation whatsoever. Though invisible, unmeasurable directly and seemingly absent, this vacuum energy may actually be one of the most important and consequential forces shaping the entire cosmos across its history. In the earliest fraction of a second after the beginning, when the universe was unimaginably hot and dense, a particular form of vacuum energy associated with certain quantum fields could have driven cosmic inflation, causing space itself to expand at speeds dramatically faster than light, growing by an incomprehensible factor in less than a trillionth of a second. This would explain why the universe appears so uniform and flat on the larger scales we can observe. Then, billions of years later, after the universe had cooled and expanded tremendously, vacuum energy may reappear in a different form or from a different source as what we now call dark energy, the mysterious pressure that is currently accelerating the expansion of the universe, pushing galaxies apart at ever-increasing rates. If these two phenomena, inflation in the first instant and dark energy today, are truly connected or arise from the same underlying physics, then the same fundamental energy that sparked the birth of the universe in its first unimaginable moment is still actively driving its evolution today, pushing galaxies apart and determining the ultimate fate of everything that exists. What we casually dismiss as empty space or pure nothingness may actually be the most powerful and consequential something in all of existence, the hidden engine driving cosmic history from beginning to end. Fact 86. Black holes may encode information on their surfaces. A profound paradox arises when physicists think carefully about black holes and the fundamental principle that information cannot be destroyed in physics. When matter falls into a black hole, crossing the point of no return called the event horizon, and disappearing from view forever. What happens to all the information that matter contained? The quantum states of all its particles, the precise arrangements and properties that defined it, all the microscopic details that specified exactly what it was? The laws of quantum physics insist absolutely that information can never be truly lost or destroyed by any physical process, yet black holes appear to swallow everything completely, erasing it beyond any possibility of recovery or reconstruction. This apparent contradiction, known as the black hole information paradox, has troubled theoretical physicists for decades. One proposed resolution to this deep puzzle, suggested by groundbreaking work connecting quantum mechanics with gravity, is that black holes do not actually destroy information at all despite appearances. Instead, they store all of it on their surfaces, encoded in incredibly subtle and complex patterns of quantum states spread across the event horizon itself. This radical idea would completely reframe our understanding of black holes, transforming them from bottomless voids that erase everything into something more like cosmic hard drives or storage devices, their surfaces shimmering with hidden quantum codes containing the complete record of everything they have ever consumed throughout their existence. The information would be scrambled, encoded, and transformed in ways we do not yet fully understand or know how to decode, but it would remain there, permanently woven into the very fabric of the horizon itself like invisible writing waiting to be deciphered by future generations of physicists. Fact 87. The holographic principle suggests reality is two-dimensional at heart. Building on profound ideas about how black holes store information on their surfaces rather than in their volumes, some of the most brilliant physicists working at the frontiers of theory have proposed something even more radical and mind-bending called the holographic principle. This principle suggests that the three-dimensional universe we experience and inhabit, with all its depth and volume and space, may actually be a kind of projection or emergence from something more fundamental, with all the truly fundamental information encoded on a distant two-dimensional surface, like a hologram that creates the convincing illusion of three-dimensional depth and structure from information stored on a flat two-dimensional plate. Just as a flat holographic image contains all the information needed to reconstruct a three-dimensional scene when properly illuminated, perhaps the entire cosmos we inhabit, with all its galaxies and stars and structure, emerges from data written on some cosmic boundary surface somewhere beyond our reach or comprehension. This profoundly strange idea arises from deep attempts to reconcile general relativity, Einstein's theory of gravity and space-time, with quantum mechanics, the theory governing the microscopic world, two pillars of modern physics that have proven notoriously difficult to unite into a single coherent framework. The holographic principle does not mean reality is fake, illusory, or somehow less than real. Rather, it suggests something far more subtle and profound, that space and time themselves may be emergent phenomena rather than fundamental, shadows or projections cast by a deeper and more fundamental layer of physics that operates according to rules and principles we are only beginning to glimpse through advanced mathematics and theoretical reasoning. Fact 88. The cosmic web keeps growing as galaxies drift apart. The large-scale structure of the universe, when mapped across billions of light-years, resembles an intricate three-dimensional web, with bright strands of galaxies linked together by filaments of invisible dark matter, and separated by vast empty voids containing almost nothing. This cosmic web is not frozen in place like a static sculpture, or a photograph captured at one moment. Instead, it continues to evolve and change dynamically over billions of years under the competing influences of gravity and dark energy. Gravity draws galaxies along the filaments, like beads sliding on strings, pulling them together into ever denser concentrations and growing clusters. Meanwhile, dark energy pushes against this contraction, driving the overall structure to stretch and expand outward, causing the web itself to grow larger with time. As billions of years pass, clusters of galaxies grow denser and more concentrated as more galaxies fall into them along the filaments, while simultaneously the voids between structures grow larger and emptier, as expansion carries their edges farther and farther apart in all directions. The contrast between dense regions packed with galaxies and empty regions containing almost nothing sharpens continuously over cosmic time. The cosmic web is alive in a very real sense, slowly sculpting itself under these competing influences, gravity pulling inward to create structure, while dark energy pushes outward to separate things. Even now, at this very moment, our own Milky Way galaxy drifts along its particular strand in this grand structure, part of a larger evolving pattern that will continue changing and developing for billions upon billions of years to come, long after our sun has died and our planet has ceased to exist. Fact 89. Galaxy filaments can stretch for 500 million light-years. Among the most breathtaking and awe-inspiring structures anywhere in the entire observable universe are the galaxy filaments, immense chains or rivers of galaxies flowing together across distances that completely challenge human comprehension and imagination. Some of these filaments extend for 500 million light-years or even more, binding thousands upon thousands of individual galaxies together in single, continuous, coherent structures that stretch across significant fractions of the observable cosmos. To put this into any kind of perspective, remember that light travelling at 300,000 kilometers per second would take 500 million years to cross from one end to the other. Within these enormous filaments, individual galaxies cluster together like luminous pearls or beads strung along invisible threads, their motions guided and controlled by the gravitational pull of vast rivers of dark matter flowing through the structure, matter we cannot see or detect directly, but can only infer from its gravitational effects. To map and visualize these filament structures spanning the universe is to glimpse the skeleton or framework of the cosmos itself, the underlying architecture and blueprint on which everything else is built and organized. These filaments reveal with stunning clarity that galaxies are not scattered randomly, uniformly or haphazardly across space as might have been expected. Instead, they are woven into vast coherent structures following clear patterns, connected together into networks that span unimaginable distances. The filaments form the strands of the cosmic web, connecting everything, together in an organized pattern so large and extensive that it can only be properly appreciated and understood by stepping back and looking at the universe as a whole, seeing the forest instead of individual trees. Fact 90. Some of the most distant quasars are powered by billion solar mass black holes. Quasars are among the most luminous, energetic, and powerful objects anywhere in the entire cosmos, capable of outshining entire galaxies containing hundreds of billions of stars from their incredibly compact central regions. They are powered by supermassive black holes sitting at galactic centers that are feeding voraciously and rapidly, consuming vast amounts of gas and stars and converting matter into brilliant electromagnetic radiation with remarkable efficiency through the process of accretion. What continues to amaze, puzzle, and perplex astronomers studying these objects is that we routinely observe quasars from extremely early epochs in cosmic history, less than 1 billion years after the beginning when the universe was still quite young, already powered by black holes containing billions of times the mass of our Sun, fully formed and actively feeding. How such enormous black holes with masses comparable to small galaxies managed to assemble and grow so incredibly quickly in such a remarkably short time remains one of the greatest unsolved puzzles in all of cosmology and astrophysics. Did they somehow grow from smaller seeds, perhaps the remnants of the first stars, far faster than our theoretical models predict should be possible? Or were they somehow born massive directly, collapsing from enormous clouds of primordial gas in the early universe without ever passing through an intermediate stellar phase? Each distant quasar we discover shining from the edge of the observable universe is a brilliant beacon from the dawn of time, its tremendous luminosity powered by a monster black hole that formed and grew faster than our current theories can adequately explain, challenging our understanding of how structure emerged and evolved in the young universe. Fact 91. The universe once glowed with plasma hotter than stars. In its earliest era, in the first few 100,000 years immediately after the initial expansion began, the universe was not cold, dark, peaceful, or anything like it appears today. Instead, it was blazing hot beyond imagination, filled with roiling plasma far hotter than the cores of even the most massive stars we observe today. This plasma was a seething soup of electrically charged particles, with protons and electrons flying freely through space at tremendous speeds, unable to bind together into neutral atoms because the temperature was far too high. Collisions between particles were constant, violent, and energetic. Light itself, photons of electromagnetic radiation, was completely trapped within this plasma, unable to travel freely in straight lines for any significant distance because it scattered endlessly and constantly off the free electrons that pervaded all of space. Imagine, if you can, the entire universe filled with brilliance so intense and overwhelming it would instantly vaporize anything we could possibly imagine, yet with no clear view in any direction whatsoever, just a glowing, opaque fog stretching infinitely in all directions without any features or structures visible. This extreme state persisted for hundreds of thousands of years, defining the young cosmos as a place of overwhelming heat, intense pressure, and complete chaos. It was a time before any structure of any kind existed, before galaxies or stars or even simple atoms could take any recognizable form or shape. Only when continued expansion finally cooled this plasma enough for electrons to settle into orbits around protons, forming the first neutral atoms, did the universe settle into a gentler and more familiar state, allowing light to stream freely through space for the first time, and allowing structures to begin slowly assembling from the cooling material left behind in the wake of that primordial fire. Fact 92. Recombination ended that plasma age, making space transparent. Around 380,000 years after the beginning, when the universe had expanded and cooled sufficiently, the temperature of the expanding cosmos had finally dropped enough for a truly profound and significant transformation to occur. The free electrons that had been scattered throughout space, constantly colliding and interacting with everything, could at last combine with protons in stable configurations, settling into quantum mechanical orbits and forming neutral hydrogen atoms for the first time in cosmic history. This transition, which scientists somewhat confusingly call recombination, even though it was actually the first time these particular particles combined rather than a recombination, was like a cosmic fog suddenly lifting all at once across the entire universe. With no more free electrons remaining to scatter photons constantly in all directions, light suddenly gained the ability to travel freely across space in straight lines without interruption. For the very first time in cosmic history, the universe became transparent to electromagnetic radiation. Photons that had been endlessly bouncing and scattering for hundreds of thousands of years could finally stream outward unimpeded, beginning their incredibly long journey across the expanding cosmos, carrying information about conditions at that moment. That ancient radiation, released in that singular moment of clearing when atoms first formed, is precisely what we detect today as the cosmic microwave background, cooled and redshifted by expansion, but still carrying information from that transformative instant. It is as though the universe took its first deep breath after a long period of suffocating chaos, opening a clear window to the future and allowing light to carry information across cosmic distances for the very first time, making astronomy itself finally possible. Fact 93. The cosmic microwave background is nearly uniform to 1 part in 100,000. When scientists create detailed, high-resolution maps of the cosmic microwave background radiation across the entire sky using sensitive instruments aboard spacecraft, they discover something almost miraculous and deeply profound. The temperature of this ancient radiation is astonishingly smooth and uniform across vast regions, varying by only about 1 part in 100,000 from place to place, an evenness almost beyond comprehension. To put this in perspective, if you measured the temperature in one direction and found it was exactly 3 kelvins, the temperature in the completely opposite direction would be 3.0003 kelvins, different by only 30 millionths of a degree. This extraordinary uniformity tells us something fundamental about the young universe. It reveals that it was mixed and homogenized to a degree that is nearly perfect, as if every region of space had somehow been in contact and thermal equilibrium with every other region, sharing energy and reaching the same temperature. And yet hidden within this remarkable and almost perfect uniformity are the tiniest ripples and variations, subtle differences in density and temperature that are barely detectable even with our most sensitive instruments. Those almost invisible fluctuations, those tiny departures from absolute perfect smoothness, amounting to the variations of only 1 part in 100,000, were the precious seeds from which absolutely all structure eventually grew over billions of years. The cosmic microwave background shows us 2 complementary and equally important truths simultaneously. It reveals a universe that was astonishingly balanced and uniform on the largest scales we can measure, and at the exact same time it shows us a cosmos seeded, with just enough variation, just enough imperfection and asymmetry to allow the formation of galaxies, stars, planets, and ultimately life itself to emerge through gravitational collapse. Without that delicate balance between overwhelming sameness and tiny differences, the universe might have remained forever smooth, featureless, and empty, with no structure of any kind ever forming. Fact 94. Those tiny differences seeded galaxies and all cosmic structure. The early universe, as revealed by the cosmic microwave background, was nearly uniform across all of space, but crucially and thankfully not perfectly so. In some places scattered throughout the cosmos, the density of matter was ever so slightly higher than the average, perhaps by only 1 part in 100,000 or even less. In other places, the density was ever so slightly lower than average by similar tiny amounts. These differences were incredibly small when they first appeared, barely noticeable fluctuations that might seem insignificant. But gravity, the weakest of the fundamental forces yet, the one that operates universally across cosmic distances, is patient and absolutely relentless over time. Over millions and then billions of years, gravity steadily amplified those tiny initial differences through a self-reinforcing process, pulling matter preferentially toward regions that were already slightly denser than their surroundings. Those regions grew denser still as material flowed inward, which made their gravitational pull even stronger, attracting even more matter in an accelerating cycle of growth. Gradually, over immense spans of time, these growing clumps and concentrations evolved into clouds of gas that eventually collapsed, then into the very first stars igniting nuclear fusion in their cores, and eventually into entire galaxies containing billions of stars and enormous amounts of gas and dust. It is truly extraordinary and almost overwhelming to realize that the vast majestic spiral arms of galaxies like our Milky Way, the enormous rich clusters containing thousands of galaxies bound together, and indeed absolutely all the magnificent structures we observe throughout the cosmos down to the smallest detail, began their existence as faint ripples in the fabric of the young universe, variations so subtle they were almost undetectable. Without those initial tiny imperfections, those minuscule departures from absolute perfect uniformity, there would be no structure at all anywhere in the universe, no stars shining in space, no planets orbiting those stars, no chemistry or complexity or life arising anywhere, and no observers like us capable of wondering about any of it. The entire richness, beauty, complexity, and diversity of everything we see in the cosmos was encoded in the faintest whispers of unevenness present at the dawn of time, written into the fabric of reality in its first moments. Fact 95. Inflation could explain why distant parts of the universe look alike. One of the strangest and most puzzling observations in all of cosmology, something that demanded explanation, is that the universe appears remarkably similar, almost identical in its properties. In all directions we look across the sky, regions of the sky that are separated by billions upon billions of light years, so incredibly far apart that light could never possibly have travelled between them in the entire history of the universe, even moving at its maximum speed, somehow look almost exactly identical when we study them carefully. They have the same temperature measured to incredible precision, the same density of matter and energy, and the same statistical patterns of tiny fluctuations. How could regions that were never in causal contact, that could never have communicated or shared information with each other in any way because they are too far apart, become so remarkably similar in every measurable property? This is known as the horizon problem, and it deeply puzzled cosmologists for decades. Cosmic inflation provides an elegant and beautiful answer to this profound mystery. Fact 96. The cosmic horizon keeps expanding, but light speed keeps us bounded. Every single day that passes, every rotation of our planet, light from galaxies that were previously hidden beyond our cosmic horizon beyond the limits of what we could possibly see, finally completes its incredibly long journey across billions of years and reaches Earth for the first time. In this very real sense, the cosmic horizon is constantly growing outward, slowly and steadily revealing more and more of the universe to our telescopes, instruments, and observations. We can observe galaxies today, capture their light and study their properties that were completely invisible to astronomers working in previous generations simply because their light had not yet arrived at Earth, still travelling across the void. This gradual expansion of what we can see might suggest that eventually, given enough time, we could see everything that exists. Yet despite this gradual expansion of the observable universe, there remains a fundamental and insurmountable boundary we can never cross, no matter how long we wait or how advanced our technology becomes. Light travels at a finite speed, about 300,000 kilometers per second, which is incredibly fast by human standards, but not infinite. Meanwhile, space itself is expanding continuously, and that expansion is actually accelerating, driven by mysterious dark energy. This combination means that galaxies beyond a certain distance, roughly 16 billion light-years away in terms of current distance, are receding from us faster than their light can ever travel to reach us. That boundary, the ultimate cosmic horizon, is not made of any physical barrier, wall, or obstruction. It is simply an inescapable limit imposed by the fundamental laws of physics themselves, the boundary between what can potentially be known through observation and what must forever remain hidden from view. The observable universe keeps expanding as ancient light arrives from farther reaches of space, but simultaneously, even more of the cosmos slips irretrievably beyond our grasp forever, as accelerating expansion carries it away faster than light can bridge the gap between us. Fact 97. Entanglement may link particles across cosmic distances. Quantum entanglement is genuinely one of the strangest, most counterintuitive, and most philosophically profound phenomena in all of physics, something that defies our everyday intuition about how reality should work based on our macroscopic experience. When two particles become entangled through interaction, their quantum states remain mysteriously and inexplicably connected, no matter how far apart they subsequently drift through space, whether separated by meters or billions of light-years. A measurement performed on one entangled particle instantaneously affects and determines the state of the other, even if they are separated by distances so vast that no signal could possibly travel between them in any amount of time. This does not violate Einstein's relativity or allow faster-than-light communication because no usable information can be transmitted this way, but it does suggest a deeper level of connection woven into the universe than we normally perceive or experience in daily life. Some scientists working at the frontiers of theoretical physics have begun exploring radical ideas suggesting that entanglement might not just be a curious quirk or oddity of particle physics in laboratories, but something fundamental woven into the very structure of the cosmos itself at all scales. It may connect distant regions of space in ways we are only beginning to understand and appreciate, possibly even providing a bridge or link between the seemingly incompatible theories of quantum mechanics and gravity. If quantum entanglement operates and persists on truly cosmic scales, connecting particles, fields, and regions across the universe, then reality might be threaded with invisible quantum links and correlations, binding particles, stars, galaxies, and perhaps even entire clusters in a subtle fabric of connection that transcends ordinary notions of distance and separation. To live in such a universe would mean existing in an intricate web of connections deeper and more fundamental than space itself, where the apparent separation between objects might ultimately be merely an illusion created by our limited perspective and our inability to perceive these deeper quantum correlations. Everything would be connected to everything else in ways we cannot directly observe, but which nevertheless shape the underlying structure of reality. Fact 98. Space-time itself may emerge from quantum information. We instinctively and naturally think of space and time as the fundamental stage or arena on which everything else happens, the basic fabric of reality that has always existed and provides the background for all events and processes. But some of the most cutting-edge, revolutionary physics being developed at the frontiers of theoretical research suggests something genuinely startling and paradigm-shifting. Fact 99. The universe is still ringing faintly with primordial vibrations. Long ago, when the cosmos was young and filled with hot, dense plasma rather than the cold, near vacuum of space we see today, pressure waves moved through that primordial material in regular patterns, like sound waves travelling through water or air, but on cosmic scales. These acoustic oscillations rippled outward from density fluctuations in the early universe, creating rhythmic patterns in how matter was distributed across space, compressions and rarefactions propagating through the plasma. When the plasma finally cooled enough for atoms to form and photons to stream freely, those sound waves essentially froze in place, becoming permanent features encoded forever in the distribution of matter throughout the universe. Today, billions of years later and long after those waves stopped propagating, we can still detect the faint but unmistakable signature of those ancient vibrations in what scientists call baryon acoustic oscillations. These are enormous ripples in the clustering pattern of galaxies when mapped across the sky, waves of enhanced structure that stretch across hundreds of millions of light-years of space. They represent the frozen echoes of sounds that rang through the infant universe when it was less than 400,000 years old. To measure and map these oscillations carefully is to hear, in a very real sense, the afterglow of creation itself, a cosmic hum or tone that shaped the distribution of structure in the early universe and continues to influence the arrangement of galaxies even now, billions of years later. Though no human ear could ever hear these vibrations directly since they operate on scales far too large and frequencies far too low, and though they stopped propagating long ago, the cosmos is still marked by them, still shaped by them, faint yet enduring, carrying across billions of years the permanent memory of the universe's first acoustic symphony, its first organized waves of compression traveling through space. Fact 100. We may never know whether our cosmos is the only one. The multiverse represents one of the most tantalizing, fascinating, and simultaneously frustrating ideas in all of science, hovering at the boundary between physics and philosophy. Various independent theories and lines of reasoning, each arising from different areas of physics, suggest that our universe, with all its galaxies and structure, might be just one among countless others existing in a vaster reality. Cosmic inflation, as we have discussed, may have created not just one universe, but endless bubbles of space, each isolated from the rest by eternally inflating regions between them. Quantum mechanics, when taken to its logical conclusions, hints at branching realities constantly splitting at every quantum event, creating new parallel universes with every measurement and interaction. Some speculative models of black holes suggest that new universes might bloom or bud on the far side of each collapsed star, born from the singularity hidden within. Yet by their very nature and definition, these other universes, if they exist at all in any meaningful sense, may lie forever and irretrievably beyond any horizon we could possibly cross or any boundary we could breach. No signal from them, no light or gravitational wave, or any other form of information could ever reach us across the barriers separating different universes. No observation we could ever make, no experiment we could ever perform, could ever confirm or deny their existence with certainty. Perhaps our cosmos is genuinely unique, the only universe that has ever existed or ever will exist, alone in a greater void. Or perhaps, equally possible, it is one tiny bubble floating in an infinite ocean of realities, most of them utterly different from ours, with different laws of physics and different constants of nature, some completely lifeless and sterile, others perhaps teeming with forms of existence and consciousness we cannot possibly imagine from our limited perspective.